Hello and welcome back. As you guessed it, since we're dealing with derivatives of vector-valued functions, we should also get some derivative rules that go with these vector-valued functions. Now, a lot of these are going to mirror rules that you already know. For instance, if we want to take the derivative of a constant vector, so if I'm, say, taking the derivative of a vector, so example, derivative of a vector like 1, 1, 1, I just get the zero vector. Remember, that's the zero vector, not the constant zero. It looks like this in 3 dimensions. Along those same lines, we have a sum rule for vectors, and that's, an easy one. It's the derivative, the derivative of the sum is the sum of the derivatives, just like it was before. I won't bother with an example here because this one's pretty straightforward. Now, another example we'll see, and so this is sort of the main thing that you have to get used to with these new derivative rules, and it comes back to remembering what the objects are that are in a particular expression. So something like f of t times u of t. Now notice here, the f of t is not bolded. This is a scalar function, so scalar valued function. And that's scaling a vector valued function. Vector valued. So for instance, something like, let's say r of t is something like 1 over square root of t squared plus 16. And then let's say that's scaling some vector that looks like, I don't know, how about t squared plus 3, or then 3t, and then how about natural log of t, something like that. So in this case, when we have a scalar valued function scaling a vector valued function like this. Now this happens when we're, say, finding a unit tangent vector. It'll happen in other situations as well. If we want the derivative of r prime of t, well, it looks like the product rule for just derivatives of scalar valued functions. And it really is that. We just have to remember to keep distinct scalar valued functions and vector valued functions. So if we're doing something like this, we need the derivative of this 1 over square root of t squared plus 16, right? This is like our f of t. And then here is our, we'll say u of t. Right, so for the derivative of this, it's the derivative of the first, the scalar valued function, times the original vector valued function, plus the derivative of the scalar valued function times the derivative of our vector valued function, is the idea. So something like this, we would apply this product rule to. And then, of course, I'll skip 4 for now, we have vector products. So we can also take products of vector valued functions. So something like this. And remember, we have dot products and we have cross products. So the dot product, again, it's going to look just like the product rule from, say, Calc 1. Derivative of the first dot the second plus the derivative of the second dot the first. Now here I can say it like that because order doesn't really matter. So this works out just fine. We get out a scalar, right? The output of this should be a scalar valued function. Because remember, dot products take 2 vectors and output a scalar. When we're doing the cross product, we have to be especially careful when applying the derivative rule to this. Again, it looks like the derivative rule for products, but remember with the cross product, we really need to keep the order intact. So it looks like derivative of the first cross the second, so do this cross product, plus the first cross the derivative of the second, right? So notice how we're keeping the order intact. U prime v, u v prime. We got to keep that order. And then lastly, I'll talk about rule number 4 here, where we have a scalar valued function u, and we're putting a vector valued function inside of it. So we're composing a scalar valued function with, we're composing, a scalar valued function with a vector valued function. So something like if I have, let's say, so I'll draw an arrow up here so you know what I'm talking about. So example, let's say I have something, I'll define my u of t here. Maybe this is describing the motion of some particle. Maybe it looks like natural log of t, e to the t, and then, I don't know, something like t squared. And then maybe we want to change around our parameter a little bit. We'll see we'll want to do this in some cases. So maybe my f of t is something just like t squared. So a nice scalar valued function. If I want the derivative, so if I have r of t equal to the composition of those two, so that is u evaluated at f of t. So that would look like what? That would look like natural log of t squared, e to the t squared, and then what? T to the fourth. So I could actually do that composition and then take a derivative, or I could use this this sort of chain rule for these things, right? So I could find the derivative of u, right? So u prime of t would look like 1 over t, e to the t, and then 2t. And I could find the derivative of my scalar valued function, so this is going to be 2t. And then the chain rule says to combine them like this. Do u prime of f of t, so I'm going to stick t squared in for t here, so u prime of f of t looks like, so this is, I'm finding the derivative of r prime of, finding the derivative of r here, u prime of f of t scaled by f prime of t is the combination. So u prime of f of t, that's going to be 1 over t squared, e to the t squared, and then finally 2 times t squared. And then multiplied by the derivative of the inside, which is 2t. So this would be times 2t. So now I can bring that 2t through. So what I really get here, I'm going to get what? 2 over t, because t's are going to cancel. And then I'm going to have 2t e to the t squared. And finally, I'll have 4t cubed in the last component. So I get something that looks like this, and that's the derivative of r, which was the composition of those two. So I can use this rule, or I can evaluate the composition and then take a derivative. You'll notice we should end up with exactly the same thing as we have here. All right, so those are some derivatives we'll be using. Oh, I'd like to remind everyone at this point, right, no one sort of declared these to be the rules of derivatives for vector valued functions, right? Each one of these is deducible from previous facts and rules. So the idea is we should be able to prove any one of these things. We should be able to actually prove that using our rules for limits, what we already know for derivatives of vector valued functions, and then derivatives of scalar valued functions using rules there. For instance, let's take a look at an example there. Let's prove the dot product rule. So I want to prove that the derivative, d dt, of the dot product of two vector valued functions is derivative of the first dot the second plus the first dot the derivative of the second. So I want to prove this. Well, how do I actually know this is the rule, right? How do we deduce this? Well, when I'm doing the derivative of a dot product of two vector valued functions, the only way to really do this before we have this dot product rule is to just evaluate the dot product and then take a derivative. So let's do that. So u of t dot v of t will look like, and here I have my u and v defined like this in component form. So I'll actually take a dot product of these. Remember how to do that. We multiply the components together, v1 of t, and add them up. 2 of t, v2 of t, finally plus u3 of t, v3 of t. And let's take a derivative of this. So I'll take a derivative of this and a derivative of this. And you notice now this is a scalar valued function. So I know how derivatives rules work here, right? These are all just scalars. So we go back to Calc 1. I have a product of two scalar valued functions, and so I get out derivative of the first times the second, and it really is multiplication between scalars there, plus the first times the derivative of the second, v1 prime of t. And I'll do that for each one. So that's u2 of t, derivative times v2 of t, plus u2 of t times v2 prime of t. And I do want to get everything here, so bear with me. u3 prime of t times v3 plus u3 times v3 prime, right? There's of t's there. I was just running out of room, so I suppressed them. And let's see. So I'd like to say that this is a sum of two dot products. Let's see if we can encounter this dot product anywhere. So notice I have u1 prime v1t, u2 prime v2t, and u3 prime v3. So u prime, right, if I just think about u prime of t, this looks like u1 prime of t, u2 prime of t, u3 prime of t. And same thing for v as well. Looks like this. And so what I have here, u1, u2, u3, u1 prime, u2 prime, u3 prime, and then v1, v2, v3. So what those three represent is the dot product of u prime of t dotted with v of t. That's that blue, those blue ones now combined back into a dot product. And then I have u1 with v1 prime, u2 with v2 prime, and u3 with v3 prime. And what is that other than u of t, right? Because we don't have primes on those, times, and that's scalar multiplication, times v prime of t. And those are those green guys. So we really can work out exactly this dot product rule just by using the rules we know from Calc 1, just rules of scalar valued functions. And my claim is that you can do that for each of these. I'm not going to go through every last example, but we can recover each of these and actually prove them to be correct. All right, let's finish just with an example. Let's compute some derivatives. So here I'm given u and I'm given v. These are given in ijk form. And I want derivative of v of t squared. So by the chain rule, right, I have a scalar valued function, t squared, inside of a vector valued function. So what I can do is derivative of the outside, v prime of t, evaluated at the inside. So this is going to be v prime of t squared. So all those mnemonic devices, the sayings from Calc 1, are still the same sayings. But we just have to remember what's a vector, what's a scalar. That's sort of the important thing here. So derivative of outside evaluated at the inside times the derivative of the inside. So that's 2t. And now I can look at v. Where's my v? Find v prime of t and evaluate that at t squared. So let's maybe do v prime of t up here. So v prime of t will be what? Cosine of t in the I direction, minus 2 sine of t in the j direction, minus sine of t in the k direction. So v prime of t squared, I'm going to get by evaluating these at t squared. So I'll get cosine of t squared in the I direction, minus 2 sine of t squared in the j direction, minus sine of t squared in the k direction. And then don't forget about the derivative of the inside, everything here multiplied by 2t. So again, I could distribute that through to each component. That's fine, or I could leave it out here like this. That's also fine. Depends on what we need it for. So there's our sort of funky chain rule. And now here's our sort of funky product rule, right? Scalar valued function times vector valued function. Again, the mnemonic device works. Derivative of the first times the second plus the first times the derivative of the second. So that's going to be 2t times v prime of t plus t squared times v, the first times the second. No, this should not be v prime. This should just be v times the derivative of the second, right? Like this. And so what do we get? 2t times this. So I'll bring my scalar through here. So I'll get 2t sine of t in the I direction plus 4t cosine of t j direction plus 2t cosine of t in the k direction plus t squared times v prime. So that's t squared times cosine of t I minus 2 sine t j minus sine t in the k. And of course, I could keep going with this and combine them, right? So I'll end up with something like, I'll combine each component. So I'll end up with something like 2t sine t plus t squared cosine t. And that's all in the I direction, plus, let's see, the j's combine. I have 4t cosine t minus 2t squared. Don't forget my t squared here, sine t, and that's in the j direction. And finally, the k's combine. I have 2t cosine t, so this will be plus 2t cosine t plus or minus t squared sine of t, and that's all in the k direction. And so now I have it completely combined. There's that one. Last one I'll do is the dot product of these two. And as I just showed with the proof, I have two ways of doing this. I could first evaluate the dot product. So just take dot product of these two and then take a derivative, or I could use the dot product rule for derivatives. So this will be, I'll use the dot product rule here because we have it. Derivative of the first dot the second plus the first dot the derivative of the second. All right, what is u prime? I should go ahead and get that now. I'll need that. So that's going to be derivative of t is just 1. So this is I plus 2tj minus 3t squared k. And now I can take the dot product u prime with v. So what'll that give me? U prime dot v. So that's 1 times sine of t in the I direction. So that's just sine of t. Not in the I direction, right? We're doing a dot product, so we're just multiplying. This should be a scalar here, right? Always remember what should be the output of each of these operations. We should have a scalar here, so I don't want to see ij's and k's over on this side. That wouldn't make sense. But I can do 1 times sine of t. I can do 2t times 2 cosine t. So that's what? 4t cosine t. And then I can do minus 3t squared times cosine t. So that's minus 3t squared cosine t. So there's one part of it. And then plus, I'll put this in parentheses, plus u dot v prime. So now u dot v prime. So that's going to be a t times cosine t. So that's plus t cosine t plus t squared times minus 2 sine t. So that's what? That's minus 2t squared sine of t. Finally, the t cubed and the minus sine of t. Oh, that's a minus t cubed, so that's positive t cubed sine of t plus t cubed sine of t. And there is the derivative of that dot product. Let's see, can we really combine anything here? Sure, of course we can. We have a 4t cosine t, and I have a t cosine t there. So that's, what, 5t cosine t. Do I have any other t squareds cosine t's? No, I don't have any of those, but I have a sine t. So we could, if we wanted to, let's maybe separate all my sines and cosines. Let's do it like that, just to organize this a little bit. So again, this makes 5t cosine t. And that's going to go with my other cosine t here. So let's combine all the cosine t's. So that was what? 5t cosine t minus 3t squared cosine t. So I'll do that. Cosine t. So that took care of the 4t cosine t, the t cosine t, and the minus 3t squared cosine t. And now I'll do the sines. So I have 1 sine of t minus 2t squared sine of t and t cubed sine of t. So that's going to give me what? 1 minus 2t squared plus t cubed, and that's all times sine of t. And there is my dot product of these two, or the derivative, rather, of the dot product of these two vectors is this guy. All right, so we'll use these rules a lot in this class as we move forward. We're going to be doing some hefty computations. It'll be helpful to practice these derivative rules. Okay, that's it for this video. I'll see you next time.